Hello everyone. This video will be about chapter 14, Waves and Oscillations. We will cover simple harmonic motion and we will analyze simple harmonic motion from the point of view of kinematics, force, and energy. To start with, let's consider a spring and a mass sitting on a horizontal frictionless plane. So think about this figure on the left hand side where I have a block of mass m connected to a spring, which is in turn connected to a wall. Initially, the spring is at its natural length. Now remember, when a spring is at its natural length, it does not exert any force. So at this moment shown in this picture, the block, at least in the horizontal direction, is not experiencing any force. Okay. Now consider a situation where, which is shown in this the right-hand side figure. I have pulled the block, which is connected to the spring, a little bit to the right. So initially, I've given the spring an extension of an amount x. In this situation, if you go back to our lectures from Newton's law and applications of Newton's law and think about it, then the spring, because it's extended, it's now exerting a force on the block. Remember, the surface is frictionless. So if I let the block go at this moment, it's gonna start going back toward the wall like this. And eventually, at some point, it's going to reach the maximum compression for the spring, and the spring will start pushing it back. And this process will keep going on forever. The block's going to go back and forth, back and forth. Okay. So why does this happen? Well, the spring is exerting a force which is proportional to the expansion and contraction of the spring. And as we learned in Newton's second law applications chapters, this force is actually given by Hooke's law, that is F is equal to negative k times x, where k is the spring constant and x is the expansion or contraction in the spring. Okay, now I want to think about this problem from the point of view of kinematics.
Okay, so we saw the oscillatory motion of a spring mass system in this video here, and we now want to analyze it from the point of view of kinematics. So I have actually drawn the picture of the spring and the block in 3 different positions in this notebook here, and we will analyze them kinematically. There are 3 positions, 1, 2, and 3. Position number 1 represents a fully stretched spring. So this is the fully stretched spring. Position number 2 is spring at its natural length. And finally, position 3 is fully compressed spring. Okay. So when I say that I want to analyze this problem from the point of view of kinematics, the first thing I should do is talk about my kinematic variables. So then the question is, what are the appropriate kinematic variables in this problem? So kinematic variables. So examples of kinematic variables are, for instance, position, velocity, acceleration. And in this particular case, we can talk about first the position of the block. And let's say that we denote that the position of the block with x as a function of t. And as you can see, in these 3 situations, x, which is the position of the block relative to where the spring was not contracted, it was at its natural length, that variable x is changing with time. Okay, so position of the block is a function of time, x as a function of t. The second kinematic variable that we can talk about is velocity of block, right? If you think about it, the block is moving. At position number 1, the block is probably not moving. Position number 3, the block is probably not moving. But anywhere in between, the block is moving. So this velocity of the block is also a function of time, and it's changing with time, right? And finally, can we talk about another kinematic variable? Well, position was changing with time, so we had velocity, because velocity is the time rate of change of position. And we just said that velocity of the block is also changing with time, so we can probably also talk about acceleration of the block. Acceleration, and this acceleration of the block is also a function of time. So we have our kinematic variables: position, velocity, and acceleration. Position, x as a function of t, velocity, v as a function of t, which is also the time derivative of position, and acceleration, a as a function of t, which is the single time derivative of velocity and double time derivative of position. Now you might be wondering that in these three pictures, 1, 2, and 3, there is x in 1 and 3, but there is no x in 2. Well, remember, we are measuring the position of the block relative to its position when the spring was unstretched. So in this scenario, unstretched spring, since the spring is unstretched, that means that x is really equal to 0. And in the other two situations, because we're talking about the maximum extension and compression of the spring, we may as well call this x max in both cases. Okay. Now what I want to do next is I want to try to plot the position of the block as a function of time. And remember that our 0 for the position is in position number 2. Okay. So this is my position versus time graph. Time is along the x-axis and x, or position, is along the y-axis. And note that I have not given it units, but I could have said t in seconds and x in meters. Appropriate units would be necessary for an actual real-world problem. Okay. Now if you think about it, initially at time t equals 0, which is this point here, t equals 0, x equals 0 is the origin over here. At time t equals 0, the block was in position number 1, and corresponding to that, its x position was x max. So the block started over here. After some time elapsed, so after a certain amount of time, the block comes back to the position where the spring is unstretched, so position number 2. So that's over here. So this is where the block's position or displacement is 0 relative to the position for unstretched spring. Okay, going further, after some other amount of time t, the block is now at its maximum compression, and this position we will denote it by x max, but remember it's in the opposite direction as x max at time t equals 0. So that's because the block really moved in the opposite direction. The spring is now compressed instead of being stretched. Okay, so we know this about the position, but what about what happens in the middle? So initially, if you think about it, at the very beginning in position 1, when the spring was fully stretched, the block wasn't really moving very fast. So the way x, or position, changes is actually slow until the block gains velocity. And so at that point, the block is now moving faster. So as the block gets closer and closer to this middle point over here, the change in displacement becomes more and more rapid. So you can kind of think that the change would initially be shallow, and then it's gonna increase, and it's gonna keep going like this, and then at the end it's gonna become more shallow. Okay, that's our position versus time graph. In the displacement time plot, we can mark the three positions 1, 2, and 3 like this. So this position is 1, that's 2, this one is 3. Okay, so that's the displacement versus time plot. Now, can we also plot the velocity of the block as a function of time? So in order to do that, then we will draw a different graph with time t in seconds on the x-axis and velocity v, and the units for velocity is meter per second, along the y-axis. Okay, now looking at our picture to the left, we see that the velocity of the block in 1 and 3 were 0, because at the very beginning, when I started the block off, it was at rest. So that's point number 1. The velocity at time t equals 0 is 0, and at the very end, when the spring is compressed to the most, that's when the velocity reaches 0 one more time. Alright, so that's point number 1. This is point number 3. And as the block moves from point 1 to point 3, we know that its velocity increases. But remember, velocity is a vector, so it has direction. We are looking at motion in one dimension, so we will just keep track of the direction of velocity by talking about positive and negative values of velocity. And in position number 2, the block is clearly moving toward the negative x-axis. So its velocity is increasing in the negative direction, or in other words, it's decreasing. Its magnitude is increasing, but its direction is negative. So at point number 2, that's where the block reaches maximum velocity or maximum speed. We'll call that Vmax. Okay. Now, similar to the position versus time graph, so this is point number 2. Similar to the position versus time graph, if you think about it, at the very beginning, the position versus time graph was shallow, so its tangent was nearly a line that is parallel to the x-axis. Now remember, the tangent to the position versus time graph is really velocity. So that tells us that the velocity is 0, just as we expected. At point number 1, the velocity is 0. Okay, but the velocity is decreasing. So as the velocity decreases, initially the rate of decrease of that velocity is kind of steep, and eventually it becomes shallow as the block goes closer and closer to point number 2. And then after point number 2, it starts off being a shallow curve, and then goes back to, the velocity goes back to 0 at point number 3. So that is our velocity versus time graph. So now that we have our position as a function of time and velocity as a function of time graphs, we can go ahead and plot acceleration as a function of time. So time t in seconds is along the x-axis, and acceleration a in meter per second squared, that's along the y-axis. Okay, so now if you consider point number 1, then position number 1, then we see that the block had maximum acceleration at that point, and that acceleration was pointing in the negative y direction. So this point over here with a max, that's the point that represents point number 1. And as time went on, the acceleration initially decreased. The decrease of acceleration was shallow, and then the rate of decrease of acceleration increased until the acceleration became zero. And where did the acceleration become zero? When the block had no force acting on it. So that's position number 2, when the spring reaches its unstretched length. So it's no longer exerting a force on the block. And as time goes on after that, the acceleration starts increasing in the positive direction until position number 3 is reached. And at that point, again, the acceleration of the block is a maximum, but this time it is a maximum in the positive direction. So far we have come up with our position as a function of time, velocity as a function of time, and acceleration as a function of time plots. But these are quite qualitative. So now we're going to try to make it a little more rigorous by thinking about the force that is acting on the block at some point. So we're going to move over, and I'm going to look at these three situations, the 3 positions of the block one more time. But this time we're going to talk about forces that are acting on the block. So now, whenever it's a force problem, the first thing we should do is we should draw a free body diagram. So we draw a free body diagram, and the free body diagram for this block, of course, at different instances, different forces are acting on the block, but the nature of those forces are pretty much always the same. So the forces that are acting are, first is gravity, and number 2 is normal force, and then number 3 is the spring force or spring tension. Okay, so the force of gravity is always the same, stays the same. Normal force also stays the same. Spring force depends on position of the block. So the spring force actually depends on how much the spring has been stretched or compressed. Okay, so let's draw the free body diagram. The free body diagram of the block would have the gravitational force, mass times acceleration due to gravity, pointing downward, is the normal force from the horizontal surface on the block. And these are the only 2 vertical forces. So in the vertical direction, we can essentially write N equals mg, and this is the application of second law, Newton's second law. Which tells us that net force has to be equal to mass times acceleration, but the block is not accelerating in the vertical direction, so the net force on the block in the vertical direction is 0. So that tells us the net force, which is N minus mg, has to be 0, and that's why N equals mg is what we get. Now in the horizontal direction, the spring is pulling on the block, and the spring force F is equal to negative k times x. And we know that because we know that this is a consequence of Hooke's law. Hooke's law tells us that the force with which a spring pulls on something that is attached to it is proportional to either the extension or the compression in the spring. Okay, so now knowing that, we can actually apply Newton's second law. Newton's second law of motion. Newton's second law tells us F equals ma, right? So we can take this first equation, that is F equals negative kx, and the second equation, which is F equals ma, and put them together. So that will give us ma is equal to negative k times x. Okay, but remember, acceleration. What is acceleration? Acceleration is the double time derivative of x. So A equals d2x dt2. And if I plug that in, then I have m d2x dt2 is equal to negative kx. So one can rewrite this equation m d2x dt2 equals negative k times x in a slightly different form, which we have done over here. So our new equation looks like d2x dt2 plus k over m times x equals 0. Oftentimes this is referred to as the equation of motion for a typical SHM. And essentially what we are after is to find this x. Notice that the x appears twice in this equation. It appears just as x and then two derivatives of x with respect to time. And we want to find this x as a function of time. That's our goal. Okay, so this is a second order differential equation with constant coefficients. K over m is one of the coefficients of the differential equation. And fortunately, k and m both are constants for us given the spring. The spring constant, as the name suggests, it's a constant, and the mass of the block is also not changing. So as a function of time, the only thing that is changing is this x as a function of t. Okay, so in order to find a solution to this differential equation, it kind of makes sense that if we find a function x, which when we take two time derivatives looks sort of similar to the original function, then we will be able to solve this function. So let's kind of make an assumption. We will assume that x takes the form a times sine of omega t plus some delta. Okay, so this is just an assumption, and we will see if this assumption can let us solve this differential equation. Okay, so in order to check whether this solves the differential equation, let's take the time derivative of x with respect to t twice. So the first time derivative dx dt would look like a times the derivative of sine is cosine, so cosine omega t plus delta, but there's an omega t inside, so we will get an omega. And if we take the time derivative one more time, so we get d2x dt2, that will give us a times, well, the derivative of cosine is negative sine omega t plus delta, and we already had an omega from the dx dt, but we'll get an additional omega, so we get negative a omega squared sine omega t plus delta. So now if you compare this function, the negative a omega squared sine omega t plus delta, and our original function x equals a sine omega t plus delta, you see both functions sine omega t plus delta look similar. So there's a possibility that this set of equations will solve our differential equation. Let's try to plug them in and see what we get. Once we plug in our assumption into the equation of motion for SHM, we find this relationship. So this is our original equation, and once we plug it in, we find clearly the first term has an a and a sine omega t plus delta, and the second term also has an a and a sine omega t plus delta. So these are going to fall off, and we are going to be left with negative omega squared plus k over m equals 0. And if we rearrange it, then we find omega squared is equal to k over m. So we find that x as a function of t is equal to a sine omega t plus delta solves our equation of motion only if omega squared is equal to k over m. Note that k and m are both properties of the spring mass system, and so as such they are constants in this problem. Now that we have found the position as a function of time and velocity as a function of time, we can go one step further and we can use these equations to determine A and delta. So far, A and delta are two unknown quantities in this problem. But notice that in our position as a function of time, if we put t equals 0, then we find that x of 0, x at time t equals 0 is equal to a sine delta. And similarly, if we use the velocity expression, we find that the velocity at time t equals 0 is equal to a omega cosine of delta. But we know both of these quantities, x of 0 and v of 0. X of 0 is simply the maximum value of x that we started off with. So x of 0 is this length over here, which we can call x max or x of 0, whatever you like. So we will call it x max over here. So x of 0 is x max. And what is v of 0? Well, at the initial instant, the block was not moving at all. So at the initial instant, if I put in time t equals 0, we get v0 is equal to a omega cosine delta, and this must be also equal to 0. Alright, so using these two conditions, then we can figure out that cosine of delta must be equal to 0, because that will satisfy this condition that v of 0 is equal to 0, and as well as equal to a times omega times cosine of delta. Now if cosine of delta equals 0, that means delta has to be some multiple of pi over 2 or 90 degrees, because cosine of 90 degrees is 0. So we found that delta has to be equal to pi over 2, and now we can go back to our time t equals 0 x condition. So if I put this value of delta back into that equation, we find that x max is equal to a times sine of delta, but delta is pi over 2, so that's sine of pi over 2, which gives us a. So we find that a is nothing but x max, or in other words, this is the amplitude of oscillations. So this is the maximum value that the position of the block can take relative to the unstretched situation for the spring. Okay, so that's why this is known as the amplitude. The amplitude is the same as the initial displacement of the block that we started it off with. Okay, so we now have found the full time dependent position expression. X of t is equal to x max times sine of omega t plus pi over 2. And I got this because I used the fact that delta equals pi over 2. I put it back into my position expression. Now that we know the block's position as a function of time, which is given by this equation over here, we can try to plot not just the position as a function of time, but also velocity and acceleration as a function of time. And we will do that over here. So let's look at these three plots. So the first plot over here is the position of the block as a function of time. As you can see, the block starts off at some maximum position, and the slope of the position versus time graph slowly increases and then decreases again, etc. And similarly, we can also plot the velocity of the block as a function of time and its acceleration as a function of time. These three plots have been generated for some known values of the spring constant, x max, and the mass of the block. So I've assumed that the mass of the block is 1 kilogram. The maximum extension in the spring was 1 meter, and the spring constant in this case was 1 Newton per meter. Using this information, we have plotted the position as a function of time. Position is in meters, time is in seconds, and then velocity as a function of time, velocity in meters per second versus time in seconds, and finally acceleration, which is in meters per second squared, and time is in seconds. Alright, so now we are ready to analyze this problem from the point of view of energy. Okay, so what are the different kinds of energy we should consider? Well, the spring is expanding and contracting, so there's going to be spring potential energy. And remember, spring potential energy for a spring with spring constant k and expansion or contraction x is given as 1/2 kx squared. And then we should also consider the kinetic energy of the block, because the block is moving. When the block has a speed v and its mass is m, its kinetic energy is given by 1/2 mv squared. So we will analyze this problem by drawing an energy table. So I have already drawn the structure for the energy table. There's P spring, there's Ke block, and the total energy. And this total energy is going to be the sum total of P and Ke. Okay, so in scenario 1, the potential energy of the spring is 1/2 K times x max squared, because in scenario 1, this the initial displacement of the block is just x max, the maximum value that x takes. We know that the block is at rest, so the kinetic energy must be 0, and the total energy is the sum total of these two quantities, so we get 1/2 K times x max squared. Okay, scenario number 2, the block is moving, so it has kinetic energy 1/2 mv squared. And let's call this V max, because this is going to be the maximum speed with which the block moves. And then the spring doesn't have any potential energy. Well, in scenario number 2, the spring is at its natural length. So this is the natural length of the spring. So since the spring is at its natural length, the spring does not have any potential energy. Okay, so this entry is 0. So the total is 1/2 mv max squared. And notice that the third scenario is pretty much the same as the first scenario. So again, it's the kinetic energy is 0, the potential energy is 1/2 kx max squared, and the sum total is 1/2 kx max squared. Okay, so this is telling us that if conservation of energy applies, and here remember the block is on a frictionless surface, so conservation of energy definitely applies. So conservation of energy will tell us 1/2 K times x max squared is equal to 1/2 m times V max squared. We can further simplify our conservation of energy expression. We can first get rid of the 2's from both sides of this equation, and so that will give us K times x max squared is equal to m times V max squared. And then I can rearrange this equation and write V max squared is equal to K over m times x max squared. And finally, if I take a square root of both sides, then I get V max is equal to square root K over m multiplied by x max. Now remember, this quantity square root of K over m, that's just omega. So this quantity is just omega. And we can see that by going back to our old force expressions. We found that omega squared is K over m, which also tells us that omega is equal to square root of K over m. Okay, so since omega is square root of K over m, that tells us that the maximum speed V max is equal to omega times x max. Okay, so that's the max speed, and this one is the max displacement of the block. But the max displacement is also known as amplitude of the SHM. Amplitude of SHM. Alright. So we have now checked conservation of energy and found some relationships between velocity and displacement for the scenarios 1, 2, and 3. But what happens in between 1 and 2 and in between 2 and 3? Well, conservation of energy should still apply. So let's see if that is the case. So we're going to pick some arbitrary time t, arbitrary time t, and check conservation of energy. So at this arbitrary time, the total energy of the block can be written as the kinetic energy of the block, which is a function of time, because the block is either speeding up or slowing down, so its kinetic energy is changing with its speed. plus the potential energy of the spring, which is also a function of time, since the expansion or contraction in the spring is changing with time. Okay, but note that the sum total of these two, we expect it to be the total energy to be something that does not change with time. Okay, so what's the kinetic energy of the block as a function of time? That's equal to 1/2 mv as a function of t squared, half mv squared, that's the kinetic energy, plus half kx squared. So half kx as a function of t squared. Alright, so that's the time-dependent total energy, and our goal is to show that this total energy function really does not depend on time. How are we going to do that? Well, we'll first write down our expressions for x as a function of t and v as a function of t. We don't have to reevaluate them. We can just go back to our force page, and there we know what x as a function of t is. And so x as a function of t is just x max multiplied by sine of omega t plus pi over 2. Okay? And the velocity, in order to find the velocity, we just take a time derivative of position. So dx dt is equal to x max times omega times cosine of omega t plus pi over 2. Okay, so let's take this one and that one and plug these two into our total energy expression. So that will give us E total is equal to 1/2 mass times V, which is x max omega cosine of omega t plus pi over 2. And I'm just going to square this quantity. So that's the kinetic energy part. And then we have the potential energy part, which is half k times x max sine omega t plus pi over 2. We're just plugging in these that equation and this equation into the energy expression, and I missed a squared over there, so it's the kinetic energy is 1/2 mv squared and potential energy is 1/2 kx squared. Let's simplify these equations. So we have 1/2 mx max squared omega squared cosine squared omega t plus pi over 2 plus 1/2 k x max squared sine squared omega t plus pi over 2. Now remember, from our discussion of forces, omega squared is equal to k over m. So if I go back to our forces, when we solved our equation of motion, we found that omega must be equal to square root of k over m, or omega squared has to be equal to k over m. Great, so we can use this and plug this back into our expression for the total energy, and that would give us 1/2 m times x max squared, and then omega squared is equal to k over m times cosine squared omega t plus pi over 2 plus 1/2 k x max squared sine squared omega t plus pi over 2. Great. The m's over here cancel, and notice that we can factor out 1/2 x max squared k from the two terms, and what we have left within the square brackets is cosine squared omega t plus pi over 2 plus sine squared omega t plus pi over 2. Alright, now what is cosine squared plus sine squared for the same angle? Cosine squared theta plus sine squared theta is equal to 1. So if you apply that trig relationship, then the entire term within the square brackets becomes 1, and so we get that the total energy is equal to 1/2 kx max squared. Alright, let's go back to our total energy. For the scenario 1 and 3, we found that the total energy was 1/2 kx max squared, and that was equal to 1/2 mv max squared due to conservation of energy, and we find that the total energy, independent of what time we look at, it is always equal to 1/2 kx max squared at any time. So let's summarize what we have done so far. We are studying simple harmonic motion. Our example is spring plus mass on frictionless plane. The equation of motion is d2x dt2 plus k over mx equals 0. And this leads us to find a solution. X as a function of t is equal to a sine omega t plus delta. V as a function of t equals a omega cosine omega t plus delta. And acceleration a as a function of time is equal to negative a omega squared sine omega t plus delta. We found that omega squared has to be equal to k over m. Some important parameters in this problem are the following. A, this is referred to as the amplitude of the SHM, and delta, that's referred to as the phase of the SHM. Now note that in our particular scenario, we found A and delta by considering the values of x at t equals 0 and v at t equals 0. And generally this is true that you can find A and delta by knowing x at t equals 0 and v at t equals 0, but not every problem will have the exact same result for A and delta. Another important variable is omega. Omega is referred to as the angular frequency of the SHM. In the spring mass case, we found that omega equals square root k over m. This of course will depend on what system we are looking at. Omega equals square root of k over m is specific to the spring plus mass system. Okay. Another important variable one can talk about is the time period of SHM, or time period of oscillations for the SHM, and t equals 2 pi over omega. Okay, what does this time period mean? Well, what we could do is we could start our position expression at some time t. So x of t is equal to a sine omega t plus delta. And let's evaluate the position of, in our case it's the position of the block, at some later time t plus t, where capital T is the period of the SHM. So then the above equation is just going to give us a sine omega t plus capital T plus delta, and then we can plug in t equals 2 pi over omega. So we will find sine omega t plus omega times 2 pi over omega plus delta. So the omegas will cancel and we will have a sine omega t plus delta plus 2 pi. Now if you remember your trig, then sine of something plus 2 pi is the sine of that thing. So a sine omega t plus delta is what we get back from here. How do we get that? We know that sine of 2 pi plus some angle theta is equal to sine of theta. We applied that to get this relationship. Okay, but notice that a sine omega t plus delta is what we started with, so that is equal to x of t. So this tells you that xt plus capital T is equal to xt, meaning no matter what time you started with, after the period of this SHM elapsed, you will get back the same position, right? So that means that the motion is periodic, and the periodicity or the time period of that motion is simply t equals 2 pi over omega. Few more relationships that are interesting in simple harmonic motion. First of those is the relationship between time period and frequency. So t equals 1 over f, where f is the frequency of SHM. So now with this, we can combine with our earlier relationship t equals 2 pi over omega, and then we find that f is equal to omega over 2 pi, or omega equals 2 pi f. And so the angular frequency omega is related to the frequency f. We can also combine the time period relationship with our relationship for omega equals square root k over m for the spring mass system. And if we do that, then we find t is equal to 2 pi over omega, which is 2 pi over square root k over m for the spring mass system, which is equal to 2 pi square root m over k. And this is our relationship for the time period of the spring mass system. So this is a summary of essentially most of the important relationships that we will need to know for simple harmonic motion. I hope you enjoyed this video. Please send me feedback at bbhattach@ltu.edu. Thanks a lot.